Hello, 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 and welcome back to homework 4.1. I forgot the W. That's out of practice. Also, this is page 4 for most of you, and page 2 for 6th period if you got a spiral. If you have stapled packet 6th period, then it's page 4. We're just going to finish this up before we dive into the homework. Transforming a figure by shrinking or enlarging it in this way is called dilation. Based on your thinking about how the photocopy was produced, list all the things you need to pay attention to when dilating an image. So thinking back to yesterday's thing about the photocopier, what's all the things you need to pay attention to? 1. Location of center of dilation. This is where everything is getting pushed or pulled from. 2. The scale factor. Scale factor. I'll be shortening that to SF a lot. 3. The line that connects the center of dilation to a point, to any point. How about, let's say, to any point in the preimage and scales out in a straight line to the image, the post image, which we just call the image. Okay, so that's these lines. Center of dilation. They push a point here out to here, or they push this point out to here, along the line. See, it all connects back here. They all go back to the center of dilation, and all of the image points are on a line that connects them to their pre-image point. Consider the following question. Is it possible for Burnell to locate a position to place the original photo on the paper so the enlarged image will be located anywhere on the paper that Mr. and Mrs. Donahue may select? I think so. Yes, it's possible. But what about that formula that would tell you how far from the corner to place it? Here it is. This is the width of the paper. And this is the width of the picture, pre-image. A and B. And this is actually just the fact that there's two margins. Oh no, sorry, this is the scale factor. The scale factor is 2. So this is the original picture. This is the original width of the original picture. We're going to blow it up twice as big. And then we're going to take the width of the paper and minus the blown up picture. What's left? What's left is whatever's not taken up by the picture. But notice how there's a left margin and a right margin. So we got to divide that in half. Then we'll just focus on this. But that's the final amount. But we want to know where to put the pre-image, not where the final is going to be. So we got to divide by the scale factor, which is 2 200% 2. So these two 2's are the scale factor. This one is the fact that there's just a left and a right margin. So if you wanted to generalize, we generalize some of it with the paper width could be anything, the pre-image width could be anything, but the scale factor could be anything. So if we rewrite it for the scale factor, it's A minus, I'm actually going to use SF, a little awkward, but that's all right, scale factor B divided by 2 divided by scale factor. Now we can clean this up because this is scale factor over 1. And now we have two fractions being divided. And so let's rewrite it like that. A minus scale factor times B divided by 2 divided by SF over 1. But what did your teacher tell you about dividing fractions? Flip the fraction, switch the action. Because dividing by a fraction is the same as multiplying by its flipped over fraction. So see, the bottom is SF over 1, but now I flipped it over 1 over SF. And now we multiply, and we get 1 times this group. Remember, fraction bars create groups. So we get A minus SFB over 2 times scale factor. And you might think you could cancel that, but you cannot cancel that because of the grouping. We don't know how much SF is inside this A, and these both are getting divided, so we just leave it like this. Anything else we can say about this? Oh yeah, what you'll notice is the original thing had divide by 2, because there's 2 margins, then divide by the scale factor to get the pre-image distance from the edge. But whenever you divide by something multiple times, you're getting it smaller and smaller. All of this ends up in the denominator. So look, the 2 and the SF, they just end up in the bottom together as friends. So whenever you have a stack of dividing, after the first line, everything ends up down in the denominator. It's kind of magical. All right, let's get down to some business. Some of you in 6th period don't have these pages, the retrieval. I think you have the lesson summary. No, you do not. It goes straight into the ready, set, go. So you got if you have a spiral and you're in 6th period, you have to pay extra attention. The pairs of figures below are similar to one another. Find the scale factor between the figures and find the unknown measure indicated by the letter. Okay, so similar is a great math term, but also hecka confusing, because these two shapes aren't similar. They're exactly the same, but a different size. And so when shapes are exactly the same shape but a different size, we call that similar. They're not congruent because they can't be literally placed on top of each other. They're not literally the same, but they're the same format, the same shape, but at a different scale. And so we say they're similar, but a different scale. So these are similar. They told us they're similar, right? That's important. The pairs of figures below are similar. Yeah, it says they are similar. So we already know for a fact these are similar, but different size. But if this edge is 2 centimeters and it ends up 6 centimeters, well then it must have gotten 3 times bigger. So what should this size be? 15, because it was times 3. That's the scale factor. Even this top edge is 3 times longer, but we don't know what it is over here, so we don't know what it is over there. Okay, what about this one? They said they're similar. It's already been said in the instructions, I mean. So 5 feet becomes 10 feet. We know that's times 2. Let's verify. 8 feet became 16 feet. That's times 2. 3 feet times 2. This should be 6 feet. Scale factor, and right times 2. Forgot the scale factor. Oh no, I said right there. Scale factor times 3. When figures are similar, what will you know besides the fact that they have a scale factor? We also know that all internal angles are congruent. The external ones too, but let's focus on the inside of the shape. The angles don't change, just lengths. And that reminds me of regular polygons, because regular polygons all have the same angles. Okay, I skipped the instructions for this. Consider each of the following functions represent and determine whether they are linear, exponential, or quadratic. The way we determine this is looking at the differences. So remember, this is 5. How is 5 different from 6? 5 is down 1. You have to subtract 1 to get rid of 5. But then you add 1 to get back up to 6, and then add 3, and then add 5. And now, this is really weird. What if you took a 1? How different is that from negative 1? Well, the difference, how different they are, is actually 2. 1 minus negative 1. What's 1 minus negative 1? Taking away negatives is like adding. So this is like 1 plus 1. Oh, the simplest thing, 1 plus 1. What about 3 minus 1? What's the difference there? 2. What's the difference there? 2. When the second row of these is constant, it's quadratic. Oh, I just circled the wrong one after all of that drama. No. Second differences constant. Okay, let's look here for any exponents. Let's look here for any squares. Square exponents or variable exponents, there are none. So this is linear. So it's a normal 1 power x in there. No little 2 on there. There's no exponent, that's an x. There's no 7x on here. So it's linear. This is exponential behavior. Hopefully you saw a lot of that in Algebra 1. And now, on to the real homework. Give the factor by which each pre-image was multiplied to create the image. Use the scale factor to find any missing lengths. What did you multiply by? What is a tricky one? Oh yeah, and then, so find the scale factor, and then find, okay, there's no missing lengths here, but there are missing lengths here. You gotta figure out what y is. Once you know how you got from 1.5 up to 4.5, and there's different ways to figure that out. You could look for an easier side. Maybe there's an easier side on this home plate shape that's easier to figure out what you multiply by. But the secret is, whether it's easy or hard, is you take the pre-image length. Pretend that says image. Nope, I screwed this up already. No problem. You take the image length and you divide by the pre-image length. You take where you end up at the image and divide by where you came from. And that'll tell you how many times you have to times it up to get there. If you take your final length, the image length, final, and divide by the pre-image length, so this is divide. This is the scale factor. The final image length divided by the pre-image length tells you the scale factor to multiply by. There is an easier side. You don't have to use the 4.5 and 1.5, but why not bust out a calculator and figure it out, or just think about it? Yep. Make sure you're tracking. This would actually Shrinktified. What do you multiply to get 8 down to 2? Well, follow the formula. Image divided by the preimage. Image divided by the preimage. Image length, any length in the image, divided by its corresponding preimage length. Yep. Divide where you ended up by where you came from. Corresponding. Like, you can't divide by 2 random sides. You guys already know that. You're smart enough to realize you got to be looking at the same side, this corresponding side. So, interesting, cool. Challenging, fun. Ooh, we forgot the directions here. Set. For each real-world context or circumstance, determine the center of the dilation and approximate scale factor or way to determine the scale factor. So just talk about the situations in terms of dilation. Fran walks backwards to a distance that will allow her family to all show up in the photo she's about to take. So you can, use your imagination. Here's her photo. This is 3 people. Obviously, I'm not drawing their heads because they don't fit. So then she walks backwards, and now they end up smaller, but they fit. So is the scale factor going to be a number bigger than 1 or a number smaller than 1? Are you going to multiply by a fraction that shrinks everything down? And where does everything shrink towards? Where on this image is everything shrinking? No hints. Maybe there's a hint. I don't know. The theater technician plays with the zoom in and out buttons in an effort to fill the entire movie screen with an image. Yeah, you've seen someone zoom in and out a image. Just try to Now this one's different. Melanie zooms in on a picture that she has on her phone by touching with 2 fingers and spreading them apart until the picture is enlarged to the desired size. So where's the center of dilation there? A digital animator creates artistic works on the computer. She's currently doing an animation that has several telephone poles along the street that goes off into the distance. Can't wait for the answer key for this one. They're going to be so cool. A copy machine is set at 300% for making a photocopy. What's the scale factor? What's the center of dilation? For each of those, all of those, up to 12, all those story problems, scale factor and center of dilation. Describe them. Describe. Or determine. And then here's the review. Linear, quadratic, or exponential. Do your best, and then look at the answer key. All right. Welcome to the new semester. Doodaloo.